Welcome to the deep dive. Our mission today is pretty specialized. We're running through advanced solution models for binary alloy systems.
That's right.
We're definitely moving well beyond the foundational concepts here and really synthesizing the key insights from a core materials thermodynamics text.
Today is all about refinement. The classic models, ideal and regular, they're great starting points, but they're just too simple for real materials.
Right.
So we need to look at how to bring in composition-dependent interaction parameters, and this is the big one, how to account for atomic ordering using the long-range order parameter.
That all leads up to the Landau theory of phase transitions, right?
Exactly. It gives us this powerful, generalized physics framework.
That sounds like a journey from, well, simplified chemistry to some
Yes.
deep physics.
Yeah.
Let's start where it always begins. The ideal solution model. If we're talking about alloys, what's the core assumption that defines this model?
The defining characteristic is just a total assumption of no interactions between the constituents.
None at all.
None. Whether you're dealing with a solid, a liquid, or a gas, the only thing driving the mixing is purely statistical. It's just entropy.
So the Gibbs free energy of mixing is just a function of temperature and that entropy of mixing.
That's it.
So if the whole system is driven by entropy, that, urge toward randomness, what does that tell us about stability when we heat the system up?
Well, since the entropy of mixing is always positive for any mixture, cranking up the temperature makes the Gibbs free energy more and more negative.
Which means more stable.
Exactly. It just drives the system toward a complete, totally random distribution of atoms. The hotter it gets, the more stable that random solution becomes.
But the textbook points out this crucial theoretical problem. When you approach absolute zero, 0K, what happens to our ideal solution then?
Right. At 0K, the Gibbs free energy of mixing just drops to zero. Exactly zero, no matter the composition.
So it's
Theoretically, yes, the system would just remain in whatever highly mixed or degenerate state it happened to be in. There's no energetic reason for it to change. But then you bring in the third law of thermodynamics, and the third law says the system should spontaneously unmix into pure A and pure B components, because only those pure phases have zero configurational entropy at absolute zero.
okay. That gives us a really crucial theoretical benchmark. So we leave that no interaction ideal world behind, and we introduce the regular solution model. This is the first, practical step toward non-ideality. What's the key addition here?
We add an energy term. It's a single constant interaction parameter, and it represents the excess Gibbs free energy.
And in the regular model, that's just the same as the enthalpy of mixing, right?
Exactly. And the key constraint, the thing that makes it regular, is that this interaction parameter has to be constant. It can't change with temperature or composition.
So how does that constant interaction energy, let's call it alpha, how does that determine what the phase behavior is going to be?
Well, if that alpha term is positive, it means mixing is energetically unfavorable. It costs energy.
So things want to separate.
Right. And that drives the material toward phase decomposition. You get that classic symmetrical phase diagram where above a critical temperature, Tc, everything's a single solid solution, but below Tc, it splits into two distinct enriched phases.
And I'm guessing the size of that alpha constant dictates how high that Tc is.
Precisely. It sets the energetic limit for phase stability.
Okay, so what about the other side of the coin? What if alpha is negative?
A negative alpha means the enthalpy of mixing is exothermic. It actually helps stabilize the solution.
So it releases energy to mix.
Yes, and that pulls the free energy curve way down, well below the ideal curve, so it strongly favors a homogeneous single solution. This is a big hint that we're looking at atomic ordering, not decomposition.
So now we've hit the big limitation of the regular model, that perfect symmetry. Real-world alloys are almost never this perfect parabola centered at 50-50. So to model that asymmetry, we need the subregular solution model. What's the mathematical tweak here?
The tweak is subtle but powerful. We let the interaction energy vary with composition.
So alpha isn't a constant anymore.
Not anymore. We expand it by adding a term that depends on the molar fraction of one of the components. So we introduce a second empirical constant, let's call it B, to manage this new asymmetry.
Okay, and this is where it gets really interesting for me. We've added this variable B that's basically just a curve-fitting parameter. But what physical flexibility does this empirical change actually bias.
It buys us an incredible amount of complexity and, real-world behavior. The single most important result is that the enthalpy of mixing, the thing driving all the non-ideal behavior, can now change sign within the composition range.
Wait, hold on. You're telling me that the mixing can be exothermic in a material when there's, say, 10% of component B, but endothermic when there's 90% of B, all in the same alloy system.
Exactly that. And this duality is critical.
Wow.
It means a single phase diagram can show atomic ordering at one composition, where the negative enthalpy favors specific AB bonds, and phase decomposition or clustering at another composition, where a positive enthalpy forces everything to separate.
Something the regular model with its constant alpha could just never do.
Never.
Okay, that really clarifies why we had to break the symmetry. Let's try to ground this in a more physical reality now with statistical mechanics. We're shifting to models based on near-neighbor interactions. How is the energy of the solution determined here?
It's really intuitive. The total energy is determined by just counting the bonds. It's the sum of all the AABB and AB bond energies weighted by how many of each bond type you have.
So the enthalpy of mixing is just the energy of the mixed bonds minus the energy of the pure bonds.
That's all it is.
And the condition for ideal mixing in this context is surprisingly simple, isn't it? It doesn't mean all the bond energies are the same.
Correct. For the enthalpy to be zero, which is ideal mixing, all you need is for the energy of an AB bond to be the exact average of an AA and a BB bond. It's a much less strict requirement than saying all interactions have to be identical.
But this statistical model only works for small deviations from ideal. And that's because it makes one huge simplifying assumption. Random mixing. What's the consequence of assuming everything is random?
Well, that assumption of random mixing mathematically forces the statistical model right back into the exact same framework as the regular solution model.
Ah, so it's a circular argument in a way.
It is. We end up defining an interaction parameter, often called W1, based on how far the AB bond energy deviates from that ideal average. The enthalpy of mixing then just becomes proportional to that W1 and the product of the concentrations.
So the random mixing assumption completely falls apart if W1 is large. Why?
Because if that interaction energy W1 is significant, the system will actively choose a configuration that's energetically better than random.
It's not passive anymore.
Right. If W1 is negative, it's favorable to have AB pairs, so it will try to maximize them. That's ordering. If W1 is positive, it's unfavorable, so it will minimize them. That's clustering. The final state is always this battle between minimizing energy and maximizing entropy, or randomness.
And temperature pushes it towards randomness.
Well,
okay, so since ordering is a real phenomenon, and the random mixing assumption breaks down when ordering is strong, we have to introduce a new variable to actually track that non-random configuration. Enter the long-range order parameter, eta.
And eta, or EAT, is our crucial thermodynamic variable now. It's a measure of the degree of correct occupation. For a given lattice structure, say, going from a disordered body-centered cubic to an ordered CSCL structure, we're basically tracking what fraction of sites are occupied by the correct atom type.
Right. So if eta is 1, you have perfect order, and if eta is 0, you're completely random.
Exactly.
What happens to our thermodynamic terms once we start including eta in the math?
They change dramatically. First, the enthalpy of mixing isn't just about concentration anymore. It now includes a term that's proportional to the square of the order parameter, eta squared.
What does that mean in practice?
For a fully ordered equiatomic alloy, this new expression gives you an enthalpy that is twice as negative, twice as favorable as the old random mixing assumption ever predicted. It's a huge effect.
And crucially, how does eta fix that third law problem we had at 0K?
By explicitly including eta in the calculation for the configurational entropy. When the alloy is fully ordered, so eta equals 1, the configurational entropy correctly goes to 0.
Which is exactly what the third law of thermodynamics demands.
It is. This allows us to find the equilibrium order parameter at any temperature by just minimizing the total Gibbs free energy, which is that balance between the enthalpy and the entropy times temperature.
Okay, let's zoom out from specific alloys for a moment and look at the general physics of these transformations. This is where Landau theory comes in. What's the fundamental idea behind the Landau expansion?
Landau's insight was that you could characterize any phase transition, atomic, magnetic, whatever, by looking at how the excess free energy changes right around the critical point. He proposed expanding that excess free energy as a power series in the order parameter, eta.
So you're breaking down the excess free energy into these terms like eta squared, eta cubed, eta to the fourth, and so on.
Precisely. And the real key to understanding the transformation is the coefficient on that first term, the eta squared term. That coefficient is usually temperature dependent. It tracks the difference between the current temperature and the critical temperature, TC.
So the sign of that eta squared coefficient determines the stability of the disordered phase.
Absolutely. If you're above TC, that coefficient is positive, and the free energy curve has a minimum at eta equals 0. The disordered state is stable.
Okay.
But as soon as you drop below TC, that coefficient flips and becomes negative. The curvature at eta equals 0 flips to a maximum, making the disordered phase totally unstable. The system is forced to form an ordered phase.
Let's use this to classify transitions. The simplest case is the 2-4 model. The free energy expansion is perfectly symmetrical, using only the eta squared and eta to the fourth terms. What kind of transition does that predict?
It predicts a second-order transition. This is a continuous transformation. The key signature here is that the equilibrium order parameter varies smoothly and continuously as you cool below TC.
Okay, and for us as material scientists, what's the most important takeaway from that? What does it mean for something like latent heat?
It means there is no latent heat of transformation.
Wow.
Since the enthalpy of the system is continuous through TC, you don't need a sudden input or output of energy to jump between the states. Instead, the transition is marked by a finite discontinuity, a sharp jump, in the excess heat capacity at TC.
Okay, now what if we break that symmetry? We introduce an odd term, specifically the eta cubed term. Now we have the 2-3-4 model. How does adding that one odd term completely change the transition?
It forces a first-order transition. A first-order transition requires that the ordered and disordered states have the same free energy at the equilibrium temperature, T0. And that asymmetry means the system is no longer pinned to a single transition temperature.
And this sounds like where metastability comes into it.
This is the thermodynamic bedrock of metastability. The 2-3-4 model introduces two distinct instability temperatures. Ti minus, which is the limit for the disordered phase when you're cooling, and Ti plus, the limit for the ordered phase when you're heating.
And the equilibrium temperature is between them.
Right. Because Ti minus is less than T0, which is less than Ti plus, you can actually supercool the disordered phase below its equilibrium transition temperature. This is the fundamental reason we see superheating and supercooling in materials.
That makes perfect sense. But what if we keep the symmetry? We use the eta squared, a negative eta to the fourth, and a positive eta to the sixth term. This is the 2-4-6 model. Does symmetry automatically mean it's a second-order transition?
Surprisingly, no. Even though that free energy curve is symmetrical, the balance of those coefficients forces it into a first-order transition at T0.
How does that work?
At that transition temperature, the curve has 3 minima, all at the same free energy level, the disordered state at eta equals 0, and 2 opposite ordered states. And just like the 2-3-4 model, this case has distinct instability temperatures that allow for metastability, which confirms its first-order nature.
Okay, so pulling all of this together, from subregular to Landau, what's the practical takeaway for, the material scientist trying to understand phase stability?
I think the key is differentiation. The progression of these models lets us handle complexity, asymmetry, and non-randomness. The Landau framework, for all its simplicity, gives us a universal language to classify phase changes. It lets us distinguish between continuous second-order transitions with no latent heat and discontinuous first-order transitions with latent heat and metastability. It helps us predict not just if a transition will happen, but how.
That's immense utility.
But we started our ideal discussion with a caveat, and I think we have to end our Landau discussion with one too. There's a serious thermodynamic flaw in these simple Landau expansions, isn't there? There is, yes. While including the order parameter gets the entropy to 0 at 0K, which is great, the simple Landau models we discussed still predict that the slope of the order parameter versus temperature curve is non-zero as you approach 0K.
And the third law says?
The third law strictly requires that this slope must go to 0 at absolute 0. It's a known boundary condition failure of the generalized theory right near the ground state.
That was a really powerful deep dive. We went from the simplistic baseline of ideal and regular solutions through the necessary asymmetry of the subregular model into the physical basis of statistical mechanics, and finally all the way to the generalized physics of Landau theory.
And remember those key concepts. The subregular model's ability to handle both ordering and clustering, the physical need for the atomic order parameter, and those distinct thermodynamic signatures like the heat capacity jump versus the latent heat that really defines second and first order transitions.
We really hope this technical summary helps you solidify these critical concepts for your studies and your work. And here's a thought to leave you with. If the slope of the order parameter must be zero at absolute zero, what unknown physical mechanism dominates at those ultra-low temperatures to enforce that final compliance of the third law? Until next time, keep diving deep into the material.